integral from 2x squared minus x plus 5 divided by x dx. Good. So because the denominator is just one term, I will separate the fraction into 3 fractions. And at the same time, simplify each fraction by itself. So 2x squared over x is 2x. X over x is -1 with minus in front, plus 5 over x. So what we did first was to separate this fraction with a trinomial in the numerator as the first term over the x denominator, second term, third term. When I simplify 2x squared over x, I get 2x. When I simplify x over x, I get 1, but there is minus in front. And then 5 over x has to stay as is. So at this point, I have 2x squared over 2 minus x plus 5 natural log of the absolute value of x plus a constant c. So I copy 2. When I differentiate this function, I get x. When I differentiate this function, I get -1. When I differentiate this function, I get 5 over x. So I'll simplify a little bit more. So x squared minus x plus 5 natural log of the absolute value of x plus a constant c. I wrote it one more time so it's completely cleaned up. Oh, I'm so sorry. I'm so sorry. Oh, I'm so sorry. Should I start from the beginning? Shauna, were you able to see it? Not really, right?
That's all.
Okay, so again, 2x squared over x is 2x, x over x is 1 with minus in front, and 5 over x. So now 2x squared over 2, because the derivative of this is x, minus x, because the derivative of this is 1 or minus 1, and 5 natural log of the absolute value of x, because the derivative of this is that, and of course plus a constant c. And then in the next step, I just simplified it a little bit. So I simplified the 2, so I have x squared minus x plus 5 natural log x plus c. Is this okay? Is this okay? Better? Okay. Is there anything else? Is there anything else that we need to go over?
We go over number 50?
Yes, of course. Is it from the same page?
Yes.
Good. So let's share here. 50/50 right here. So we have same page, so 392. So we have f prime of x equals x squared plus 1. And we are told that f of 0 is 8. We cannot use this information because we do not have f yet. So then we know that f of x will be x to the third over 3 plus x plus a constant c. How come? When I differentiate this piece, I get x squared. When I differentiate this piece, I get 1. And when I differentiate this, I get 0. But now I'm told that when x is 0, 0, 0, the function is 8, which means that c is 8. So now I have the unique function, x to the third over 3 plus x plus 8. And this is just one function whose derivative is guaranteed to be this and also passes through the point 0 for x, 8 for y. Is this okay? Anyone? Okay, is there anything else we need to look at? Are there other questions? Anybody? Is there anything else? Okay, then if you do find something, please stop me anytime. So we're going to go back to 4.2. So in 4.2, we started, I'm just going back to the notes just to refresh your memory. So let me write something very important. Let's recap. First of all, there are only two types of integrals. There are two types of integrals. One which is indefinite, and the other one that is definite. So far, we dealt with the indefinite. What was the indefinite? Something like, as an example, the integral, the indefinite integral from, let's say, x squared plus 1 dx. And we obtained x to the third over 3 plus x plus a constant c. We like to denote this, or at least the function, f, uppercase F of x, plus a constant c. So the general form that we should look at is the integral from f of x dx equals f of x plus a constant c. This is what we call the most general antiderivative. It's a family of functions. All these functions, all of them, infinitely many, have the same derivative. So again, when I differentiate this side, f of x plus c prime, I will always get f of x. This is what we looked at so far. So we also know, and I'm going to write this down as well, an indefinite integral has a result, a function, or a family of functions, or the most general antiderivative. So again, I'm also going to write that in here just to make it super clear. The definite integral, indefinite integral equals a function or a family of functions. Or the most general antiderivative. So the indefinite integral will always give us a family of functions or the most general antiderivative. This is what we looked at so far. And this is how we like to write it. We like to use this notation, uppercase. What is this? Is the antiderivative of f of x. In other words, when I differentiate this function, I get this function. When I differentiate this function, I get this one. Okay, now let's go to the other side. We have not done anything here, but we looked at an example, but we did not calculate. We don't know how to calculate it yet. So what is a definite integral? Something like this. Remember, this is the sum s, but it's a stretched s because a regular s will not work. So the definite integral from a number to another number, the definite integral from a to b, from f of x dx equals, and I will teach you how to calculate this. So again, how do we read this? A and b are limits of integration. It doesn't mean that these two numbers have anything to do with LIM that we've been looking at for 2 months. No. It's just that we use the same word. So the definite integral has limits of integration, the lower limit and the upper limit. What do they mean? It means that x is in the interval a comma b and not nowhere else. That's all it means. So the definite integral from a to b, from f of x dx, it will be calculated, and it's a number. It's not a function. It's not a family of functions. It's a number. And how do we calculate that number? We determine the antiderivative, like before, no difference, f of x. We write a vertical bar next to it. At the bottom we put a, at the top we put b. What does this mean? What do these symbols represent? This means that I have to plug in b and then subtract when I plug in a. So f of the upper limit minus f of the lower limit. What does this mean? I'll explain in a minute, but I just want you to know that this is called the definite integral from a to b from f of x dx equals f of b minus f of a. This is called fundamental theorem of calculus. There are two parts. This is part 2. We do not present in this class part 1. In the STEM calculus, I present both parts. I present the fundamental theorem of calculus part 1 as well as part 2. In this class, we only focus on the fundamental theorem of calculus part 2. Again, what does part 2 say? It shows us how to calculate a definite integral. How to calculate it? We find the antiderivative the same way we did it before for the indefinite, but this time, after we find it, we continue our evaluation by plugging in the upper limit and subtract when we plug in the lower limit. This is how we calculate a definite integral, and this is the fundamental theorem of calculus. Okay. Before we get to, I want to come back to what we started last time. Before I show you examples on how to determine a definite integrals, we have to look at something else. And now I'm going to explain. Last time we stopped at the following example, where I was saying, calculate the area under, and I chose a very simple example, f of x equals x squared plus 1 on the interval 0, 2. And we graph the function, very simple. If you remember, this is x squared, but we have to move it up 1. So the graph is something like this. And this is 0, this is 1, and this is 2. So this is our function f of x, x squared plus 1, on the given interval 0, 2. So this is the area that we're asked to determine. And I stopped last time asking myself, so to speak, why on earth? Why? Why? Who cares? Why would I even think of determining the area under a graph? Here's the answer. Assuming that this graph, this function, is the velocity function, let's assume it is, or if you want cost function, or if you want revenue function, or profit function, if this, of course, marginal cost, marginal revenue, and marginal profit, because it has to be a derivative. So assuming that this function is either the velocity, which is a derivative of the distance, or the marginal cost, which is a derivative of the cost, or marginal revenue, which is a derivative of the revenue, or marginal profit, which is a derivative of the profit, this area represents the total distance, if it's velocity, the total cost, if it's the marginal cost, revenue, if it's the marginal revenue, or profit, total profit. So depending on what the function represents, finding the area under the graph between whatever limits we have, it will give us the total distance covered between 0 and 2, or the total cost producing between 0 and 2,000 or 2 million units, or the total revenue between 0 and 2 million units, or the total profit between whatever. That is the scope or the reason why we want to determine the area. And what will the area be? The total area, and if you want total distance, if the function is the velocity, total cost, if the function is the marginal cost, and so on and so forth. What will that be? The integral from 0 to 2 from f of x dx. If this function is the marginal cost, this number will be the total cost, and so on and so forth. Also, I mentioned something else last time. For example, if I have the integral, let's say from 0 to 2, from e, let's say x to the third, x to the third, plus 1 dx. We are not going to determine this. Several functions, in certain situations, the computer, the calculator, will determine the antiderivative. But in certain situations, we will not be able to find it. We are not capable of finding all antiderivatives. We cannot. Many of them we can, many of them we cannot. So I can still approximate. If I cannot find, let's say I cannot find the antiderivative by hand, I can still approximate this integral. How do I do that? And I'm gonna show you on this simple example. Okay, we have many methods. I will show you two. Okay, so this is our function f of x equals x squared plus 1. This is the given interval to us, 0 to 2 million, 0 to 2, whatever it is. And let's suppose we want to divide this interval into 4 equal pieces. So between 0 and 0.5, between 0.5 and 1, between 1 and 1.5, and between 1.5 and 2. On each of these intervals, I will create rectangles. Base times height. Base times height. Base times height. Base times height. As you notice, I used the height, the leftmost point. What does that mean? The height is here on the left of the subinterval. This one has the height on the left. What does this mean again? This height is f of 0. This height is f of 0.5. This height is f of 1. This height is f of 1.5. So I use the height on the left of the interval. Height, 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 height. I can also use the rightmost point. Still 0, still 0.5, 1, 1.5, and 2. They are equal pieces. How do I show that? Okay, here it is. Base times height. Base times height. Base times height. Base times height. And this is the rightmost point for the height, which means this height is f of 0.5. This one is f of 1. This one is f of 1.5, and this one is f of 2. So I have this rectangle, I have this rectangle, and this one. Is there a difference? Yes, there is a difference, of course. Can anyone tell us, looking at my graphs, which of these two is an overestimate of the correct actual area?